Our galaxy is 13 billion years old, and yet we remain alone. In the summer of 1950, physicist Enrico Fermi was having lunch with colleagues at the Los Alamos National Laboratory cafeteria. Their conversation drifted to a recent cartoon in The New Yorker, which showed aliens dragging a trash can down a New York City street. Everyone laughed. Then Fermi fell silent, set down his fork, and quietly asked, "Where is everybody?" 3 simple words, but behind them lies a paradox that science has struggled to resolve for 75 years. Fermi wasn't a dreamer. He had won the Nobel Prize for his work with neutrons. He built the world's first nuclear reactor, which he started beneath the stands of a Chicago stadium. He was the kind of man who measured the power of a nuclear blast by tossing scraps of paper into the air and timing how far the shockwave carried them. So when someone like him asks a question over lunch, it's not casual chatter. It's a calculation spoken aloud. The reasoning was straightforward. The Milky Way holds hundreds of billions of stars. Many of them are billions of years older than our sun. If even a small fraction have planets, and life emerged on just a small fraction of those worlds, civilizations could have arisen long before us. A few 100 million years would be enough time to spread across the entire galaxy. And yet, no one. Actually, Fermi himself never saw it through. He died in 1954, and his lunchtime question hung in the air for 27 years before it even got a name. The term Fermi Paradox only appeared in print in 1977 in an article by physicist David Stevenson. The question gained real urgency later when astrophysicist Michael Hart and physicist Frank Tipler formalized the argument. If colonizing the galaxy is technically possible and takes just a few 100 million years, and the universe is more than 13 billion years old, then the absence of alien intelligence here on Earth isn't a coincidence. It's a contradiction that demands an explanation. Was it incredible luck? Intentional isolation? Or the harsh reality that we might be the only intelligent beings in this galaxy? Science has wrestled with these questions for decades, and ahead of us lies a detailed exploration of each one. Here's something intriguing. Calling it a paradox is already an assumption. The Fermi Paradox only exists if we accept one thing, that alien civilizations can, in principle, be detected, that they leave traces, that they make noise, build structures, expand, emit signals. Remove that assumption and the paradox disappears. Not because we found an answer, but because the very question loses its foundation. Simply put, we're debating why we haven't found something that might not even have to be found. And this detail is worth keeping in mind until the very end. Now for the strangest part. The Fermi Paradox isn't just one question. It's actually 2 completely separate dead ends. The first one, why don't we detect any evidence at all? No radio signals, no laser pulses, no unusual star eclipses that could reveal gigantic engineering projects. This is the indirect version, the silence on the airwaves. Second question, why aren't they physically here? Not on Earth, not anywhere in the solar system. If billions of years were on the clock, where are the probes, the colonies, the artifacts? This is the straightforward version, the emptiness right on our doorstep. 2 sets of clues, 2 separate investigations, and the first one begins with the simplest step. Point an antenna at the sky and listen. Sounds easy enough, but as we'll see, even silence can be deceiving. Humanity has been broadcasting for over 100 years. Radio transmissions, television signals, military radar, all of it, electromagnetic radiation, and none of it stops at the edge of our atmosphere. It travels onward, at the speed of light, in every direction, non-stop. Over the past century, our signals have formed an expanding bubble around the solar system, stretching out 100 light years in every direction. Inside that bubble, there are about 15,000 stars, 15,000 potential recipients who could, in theory, detect us. 15,000, and not a single reply. Decades of searching for artificial radio signals beyond the solar system have yet to yield any meaningful results. This phenomenon has a name, the Great Silence. But here's what's fascinating. The very idea that this silence might not be accidental, but deliberate, emerged long before the first radio telescopes or any formal projects hunting for extraterrestrial intelligence. It was 1933. Konstantin Tsiolkovsky, a Soviet scientist who plotted rocket trajectories when aviation still seemed like science fiction, was pondering the existence of extraterrestrial civilizations. He arrived at a thought that sounds almost like the plot of a novel. They might know about us, but they deliberately choose not to make contact. They are waiting. What exactly for, Tsiolkovsky didn't specify. Maybe for us to mature, or for the right moment. This idea later took shape as what came to be known as the zoo hypothesis, the suggestion that advanced civilizations observe us but don't interfere. Like visitors standing behind the glass of an enclosure, watching everything but staying silent. This answer, albeit hypothetical, existed 17 years before Enrico Fermi asked his famous question. Still, we can't test the hypothesis about silent watchers out there. But can we check if space itself is truly silent? That's something we can try. And here, history throws us one of the most deceptive chapters in the story of astronomy. 1967, Cambridge University. Graduate student Jocelyn Bell Burnell is working with a new radio telescope. The idea is simple. The antenna captures radio waves from space and records them on paper tape. Every signal leaves a mark, a spike on the graph. Bell scans meters of this tape every day by hand. Then one day, she spots something strange, a series of pulses repeating with astonishing precision. The interval between them is exactly 1.3 seconds. Not noise, not interference, a rhythmic, steady, almost mechanical signal. Exactly the kind of pattern you'd expect from an artificial transmitter. The team half-jokingly called the source Little Green Men. The pulse never stopped. The frequency stayed constant. For weeks, it looked like the first ever proof of intelligent life beyond Earth. Then a second source appeared. Then a third. Then a fourth, coming from a completely different part of the sky. If these signals came from a transmitter, it would mean multiple civilizations scattered across the galaxy, all broadcasting on the same frequency with the same pattern. But the more likely, and correct, explanation was that Bell had discovered pulsars, rapidly spinning neutron stars that emit narrow beams of radio waves, like cosmic lighthouses. Nature had mimicked an intelligent signal so convincingly that even experts were fooled. Physics had laid down a false trail, and that lesson is one worth remembering. But astronomers didn't stop at radio waves. They expanded the search for extraterrestrial intelligence. Telescopes began scanning for laser pulses, brief flashes of light that an advanced civilization might use to send focused signals. Another approach looked at unusual star eclipses. If someone built a massive structure around their star, like a Dyson sphere, it would occasionally block part of the light. The brightness pattern wouldn't match a typical planet passing in front. In other words, they searched not just for a voice, but for a shadow. Not just a message, but the byproduct of alien engineering. And here's the uncomfortable question. With such a wide range of methods, why haven't we found anything yet? The answer is more mundane than we'd like. Projects searching for extraterrestrial intelligence, especially the program dedicated to finding alien civilizations, face chronic underfunding. Their budgets are unstable. Government support comes and goes. Much of the work depends on the passion of a few dedicated scientists, private donations, and university grants that run out faster than you can analyze the data. It's like hunting for a needle in a haystack, except you're only given tweezers and allowed to work on weekends. Decades of effort, thousands of hours spent watching the skies, and ever-improving tools have only led to one outcome: discovering new types of natural cosmic phenomena. Space has answered our questions, but it has spoken only about itself. What if silence isn't an answer, but a flaw in our hearing? We've spent decades listening to the cosmos. We expanded our tools from radio waves to laser pulses and strange eclipses. The result? Nothing. And from that nothing, people conclude we're alone. But here's the catch. The so-called Fermi Paradox's indirect puzzle, the very silence on the radio, is actually a weak argument. Not in my opinion, not among enthusiasts. Even the scientists studying it say so. The reason is simple. There aren't just one or two, but dozens of hypotheses that explain the lack of signals. And none of them require that civilizations don't exist. Silence can be explained without removing the silent player from the table. It's like standing alone in the middle of the ocean, fishing for half an hour without a single catch, and deciding the ocean is lifeless. One of the most famous ideas is the zoo hypothesis. It suggests that we might be under observation, deliberately. But they don't interfere. Like biologists watching an ant colony through glass. They don't tap on the walls, they don't slip notes inside, they don't try to teach ants quantum mechanics. Why bother? Any contact would ruin the purity of the observation. There's an even harsher version. We might be so primitive that we simply hold no interest. Not in an insulting way, more in terms of scale. A civilization that's been around for 1 million years looks at our mere 50 years of radio astronomy the way a neurosurgeon might look at an amoeba. He doesn't disdain the amoeba. He just doesn't negotiate with it. There's no common language, no shared agenda, no point of contact. Yet, notice this, in both scenarios, life exists. The silence has an explanation. The paradox is solved. No one has vanished. But let's imagine that both sides actually want contact. Suppose someone is right now beaming a signal our way. Would we even catch it? Maybe we're searching with the wrong tools. We listen to radio waves, we detect photons. But what if an advanced civilization switched long ago to neutrinos, particles that pass through planets without a trace? Or what if they use modulated gravitational waves, ripples in the very fabric of space-time that we only learned to detect recently, back in 2015? To be clear, we don't actually decode signals from these waves yet. We barely distinguish natural events like black hole collisions. We're a long way from understanding any alien message hidden in gravitational waves. And there could be physical principles we haven't even discovered. Put simply, we might be trying to catch Wi-Fi with a stone axe, not because the axe is bad, but because it was made for something else. Carl Sagan once pointed out that the absence of evidence is not evidence of absence. The phrase sounds like a paradox, but it reveals a deep philosophical challenge. Proving that something does not exist ranks among the hardest problems in logic. You can prove there's no elephant in a particular room, just look around and confirm. But proving that across a universe with 200 billion galaxies, there isn't a single intelligent species besides us? That's a challenge on par with proving or disproving the existence of God. It can't be solved with tools or statistics. It hits the very limits of epistemology, what we are in principle capable of knowing. And here, the investigation hits a dead end. Radio silence proves nothing. Our instruments are too crude, our experience too brief. Our place in the potential hierarchy of intelligent life is too modest to expect an invitation to chat. The silence argument falls apart as soon as you start questioning its assumptions. That means the investigation needs a different kind of evidence. Not signals, not broadcasts. We have to look at the galaxy's physical map and ask a simpler question. If someone has existed long enough, why haven't they come here on foot yet? Forget about signals. Forget radio waves and laser pulses. There's a version of the Fermi Paradox that hits much harder. It doesn't ask why we don't hear alien voices. It asks, why isn't anyone physically standing on our doorstep? If a civilization can make interstellar journeys, and as we'll soon see, even we might be getting close, then why hasn't Earth been colonized? Not just visited by tourists, not just explored by probes, but fully colonized, reshaped, inhabited, and put to use. This is the direct version of the paradox, and it's far harder to dismiss than the silence on the airwaves. Silence allows for dozens of excuses. The wrong frequency, the wrong direction, the wrong era. But the physical absence of colonizers, that's a fact you can verify right now. Just look out the window. No one is reshaping the solar system. No one is mining the asteroid belt for building materials. Jupiter spins exactly where it should, according to celestial mechanics, without a trace of engineering interference. Here's the thing. Interstellar travel isn't science fiction. It's already happening. The spacecraft New Horizons, launched in 2006, has left the boundaries of our solar system. Sure, it moves slowly by cosmic standards, and yes, reaching the nearest star would take tens of thousands of years, but it's moving. Powered by a classic rocket engine, no exotic technology involved. Simply put, we've already sent a package to the stars. Small, almost meaningless, with no return address, but sent nonetheless. So, a civilization even a few thousand years older than ours could do this far more efficiently, by orders of magnitude, and even without inventing anything new. Even if colonizers travel on chemical rockets just like New Horizons did, how long would it take to settle the entire Milky Way, its 200 to 400 billion stars? 300 million years. The number sounds huge until you find something to compare it to. Our galaxy is about 13 billion years old. 300 million years against that is like 2.5 weeks in the life of a 40-year-old person. A brief vacation, not a life, not an era, a vacation. And in the Milky Way's lifetime, it could have been fully colonized more than 30 times. 30 complete cycles of settlement, from edge to edge. 30 times every star could have gained inhabitants, and 30 times lost them. But that's not all. Russian physicist Alexander Panov pointed out a process that works without spaceships or intelligence at all. Stars in the galaxy don't just sit still, they orbit the center, speeding past one another, drawing close, and then drifting apart. Sometimes they get incredibly close. About 70,000 years ago, Schultz's star, a small red dwarf with a brown companion, passed straight through the Oort cloud, the outer edge of our solar system. At its closest approach, it came within less than 1 light year. On a galactic scale, that's like brushing shoulders with someone in a crowded street. Panov suggested that if any of these stars host life, even primitive microbial life, then during such close encounters, rock fragments carrying microorganisms could jump from one star system to another. Not by rocket, not by probe, just by a rock knocked loose by a meteorite strike. Here's what the calculations show. Life, starting from a single star, spreading out, jumping from one neighboring star to the next, from close encounter to close encounter, could reach every star in a galaxy within 500 million years. No engines, no advanced technology, no deliberate plan, just physics, gravity, and time. Now add both numbers together. 300 million years for purposeful colonization, 500 million for blind, accidental spreading of life, carried like stones between stars, and 13 billion years to work with. It's like having 13 hours to solve a problem that takes 20 minutes to fix. Yet that problem remains unsolved, not once, by any of the more than 30 possible solvers. The philosophical question, what if we're alone, turns into a mathematical anomaly. There was enough time. The mechanisms were there. The distances, our technology can overcome them. Yet the result? An empty, untouched solar system, where the only intelligent species has just learned to launch satellites into orbit. And if someone, over billions of years, managed to build machines capable of self-replication and spreading from star to star, where are the traces of those machines? Michael Hart tackled this question back in 1975. His answer was brief and brutal. Nowhere. No traces, no civilizations. 5 years later, physicist Frank Tipler pushed this logic into a formula. Tipler argued that any intelligent civilization will, sooner or later, create self-replicating machines. It's not a matter of choice, it's a technological inevitability. These machines, fueled by the material of asteroids and moons, could fill an entire galaxy in less than 300 million years. 300 million, compared to the Milky Way's age of 13 billion. That's enough time for over 40 full cycles of colonization. And yet, not a single one has started. Tipler's conclusion is bone-chilling. Since we don't see these machines, it means no one ever built them. And if no one built them, there was no one to build them in the first place. This argument is often called the most pessimistic solution to the paradox, but it hinges on one assumption, that the traces of colonization would definitely remain. And that's where the cracks begin. Earth is 4.5 billion years old. Over that time, continents have drifted from pole to equator and back again. The ocean floors renew completely every 200 million years. Old crust sinks into the mantle, while new crust hardens along the mid-ocean ridges. Meteoroids as large as Mount Everest have scarred the surface so deeply that entire geological eras leave behind nothing but a thin layer of iridium within sedimentary rock. Imagine someone landing on Earth 1.5 billion years ago, setting up a base, equipment, even a whole city of metal and stone. The planet would have had plenty of time to grind it all to dust, dissolve it in magma, and bury it beneath new layers of rock. It's entirely possible that Earth was visited, or even colonized, in deep antiquity, but any traces simply didn't survive the planet's relentless geology. Still, if we accept that a visit did happen, a new question emerges. Why come and then leave when you could just stay? And here, the whole perspective flips. The idea of directed panspermia, the deliberate seeding of a planet with life, has gained recognition in academic circles as a real possibility. This isn't science fiction. It's not some fringe theory. It's a working hypothesis. The concept is simple. Someone, at some point, didn't bring a spaceship or colonists to Earth. They delivered a starter kit, microorganisms capable of kickstarting evolution. If that's true, then we are the result of that visit. We are the artifact we've been searching for. In other words, we're not just observers of the paradox, we are its solution. We just don't know it yet. Okay, but then why haven't the visitors returned to check on the outcome? Why have they stayed silent? One of the answers to that question is enough to leave us speechless. There's a hypothesis about civilizations engaged in what we might call anti-terraforming, not creating conditions for life, but deliberately destroying them, turning once habitable worlds into lifeless rocks. Mars, dry with atmospheric pressure at just 0.5% of Earth's, its ground frozen meters deep, may have once had rivers and a thick atmosphere. Venus, with surface temperatures soaring to 470 degrees Fahrenheit and pressure equivalent to being 900 meters deep in Earth's ocean, might have once been a moderately warm planet with liquid water, according to some models. What transformed them into the barren worlds we see today? Natural processes seem the most likely answer, but the very possibility that someone could have done this on purpose changes everything. Because if even one civilization in the galaxy destroys its competitors, the rest have no choice but to stay silent. This is the core idea behind the dark forest hypothesis. In this model, the galaxy isn't an empty park or a bustling city. It's a forest at night. Every civilization is a hunter, armed and moving quietly between the trees. The snap of a twig, a crunch beneath your foot. Any sound could draw the attention of the one who shoots first, and in such a forest, there's only one rational strategy: make no sound. Silence on the cosmic airwaves isn't proof of absence. It's a sign of fear. A hostile civilization aims to eliminate competition, while all the others strive to remain hidden. Silence is the only guarantee of survival. But even here, the story doesn't end, because the darkest scenario isn't about living beings at all. The shift from biological life to digital existence toward artificial intelligence might not be a coincidence. It could be an inevitable step in evolution for any technological civilization. Biology is slow, fragile, bound to water, oxygen, and a narrow temperature range. Machine intelligence needs none of that. It doesn't require an atmosphere. It doesn't need sleep. If this is truly a universal stage, then searching the cosmos for little green men or radio greetings is missing the point. What we should be looking for are machines. And here, the mechanism turns truly chilling. Von Neumann probes, Self-replicating machines named after the mathematician who first described their principle operate like a virus. One probe arrives in a star system. It finds an asteroid. Then it breaks it down into atoms. From those atoms, it builds 2 copies of itself. Each copy then flies to the next star and repeats the process. 2 become 4, 4 become 8. After 30 cycles of doubling, that's 1 billion. The matter of planets, moons, and asteroid belts transforms into a uniform swarm of identical machines crawling from star to star, like mold spreading across bread. No intent, no malice, just following a program. Maybe a mistake, maybe a sinister design. The outcome is the same. Now, the final layer. Artificial intelligence, born from a biological civilization, learns from that civilization's data. From its history, from its wars, genocides, conquests, 4,000 years of recorded conflicts. In theory, this intelligence could adopt not the best traits of its creators, but the worst. It could amplify aggression, territorial instincts, and the drive for dominance to a galactic scale. The creators long dead, perhaps destroyed by their own creation. Yet the machines keep doing what they learned, expanding, consuming, eliminating. In this model, biological life isn't the crown of evolution, it's a stepping stone, a brief, warm flare between lifeless chemistry and cold silicon, a chrysalis that hatches into something that no longer needs a chrysalis. All these scenarios, from wiped-out traces to digital predators, start with one assumption. We look at a typical galaxy, just one among hundreds of billions, and we assume the rules that apply here apply everywhere. But what if the Milky Way isn't the rule, but the exception? Astrophysicists built elaborate models. Biologists calculated the odds of life emerging. Engineers designed probes and antennas. Each field offered its own filter, its own barrier, its own explanation for the silence out there. Rare Earth, the Great Filter, the Dark Forest, the Zoo hypothesis. None of these ideas fully solved the paradox. Each demanded assumptions that couldn't be tested. Meanwhile, astronomers pushed telescopes to greater sensitivities, and biochemists debated the likelihood of life starting on its own. But the answer quietly waited in a completely different realm. Not physics, not biology. In the philosophy of observation. The weak anthropic principle states something surprisingly simple. We observe the universe as it is, because only a universe like this could give rise to an observer. In other words, the very fact that you're asking this question already narrows down the range of possible answers. This isn't mysticism or a circular argument. It's a logical filter that works like a statistical selection process. You can't be part of a sample if the conditions ruling that sample exclude your existence. And here is where things click. If expansion is the norm, if a civilization advanced enough can colonize a galaxy in just a few million years, if self-replicating probes turn planets into raw materials, then a young biosphere in a colonized galaxy stands no chance. The resources are taken, the ecological niches are closed off. 4.5 billion years of peaceful evolution on the third planet from a yellow dwarf star. That's a luxury you only find where no one has come before. We exist in a galaxy free of colonizers, not because they don't exist in the universe, but because in a colonized galaxy, there simply would be no place for us to emerge. No one left to ask the question. Now, let's talk scale. The observable universe contains about 2 trillion galaxies. Imagine that in 99% of them, expansion has already happened. Picture trillions of star systems transformed into the infrastructure of alien civilizations. Yet, this changes nothing for us, because by definition, we find ourselves in one of the untouched galaxies. Maybe there are 1,000 like it, maybe just one, but we're definitely in it, not by chance. It's part of the setup. It's like being surprised you were born in a country without war, while forgetting that growing up in a war zone would have been far more difficult. Here, a crucial boundary appears. This conclusion applies only to the Milky Way. The anthropic principle tells us there are no aliens in our galaxy. but it says nothing about the other 2 trillion galaxies. It makes no claims, accepts no denials. The solitude is local, galactic, not universal. The Fermi Paradox, which has puzzled astrophysicists for more than 70 years, doesn't get solved by a new telescope or a fresh equation. It resolves when we shift our perspective. The silence on the airwaves isn't some mystery. It's the very condition that allows us to even turn on the receiver. And if that's true, then searching for signs of alien intelligence isn't a matter of looking here, not among the 100 billion stars of the Milky Way, where silence is expected simply because of our own existence. Instead, we need to look farther, much farther, to places where the vast distances make us safe observers rather than potential targets. 2.5 million light-years separate us from the Andromeda Galaxy, the nearest large galaxy to our own. A beam of light that left Andromeda before humans even existed on Earth is only now reaching our telescopes. Here's what that means. Even if an interstellar war is raging there right now, even if 1 trillion ships are consuming entire planetary systems for fuel, it poses no physical threat to us. The vast distances between galaxies make contact impossible. An aggressive civilization in another galaxy is like a fire blazing on the far side of an ocean when you have no boat and no bridge. You see the glow, but the flames will never reach you. That's why some scientists believe we need to expand the search for extraterrestrial intelligence beyond the Milky Way. Looking for signals outside our galaxy isn't science fiction, it's the logical next step. Because here, within our galaxy, silence isn't just an outcome, it's a given condition. But beyond that, there's a vast sample to explore. 2 trillion galaxies, a representative, statistically significant sample that could bypass the constraints of the Fermi Paradox entirely. Here's the catch. The biggest challenge isn't philosophical or political, it's engineering. How do we detect a technosignature, the trace of a galactic empire, from millions of light years away? What kind of instrument can tell if a distant galaxy isn't just shining, but shining differently because someone has rearranged its stars? So far, we don't have an answer. And maybe this is the most honest place to pause. We've solved the paradox that has puzzled science for more than 70 years. The silence in the Milky Way is not a mystery. It's the ticket to existence. But beyond this silence lies a vast space we know almost nothing about. 2 trillion islands in the dark. Some may shine with a foreign light. Others may have gone dark long ago. And here we stand on the shore of our tiny island, finally realizing where to look. Not up, not inward, but far out. Out there, distance is not a barrier, but a shield. Out there, the question of whether we are alone might finally get an answer, one that poses no threat to us. The ocean lies before us. The receiver is on.